Now, very important result for strongly connected components. See this. In directed graph, what you do, can you notice one thing? If you notice, strongly connected component is like a team. Okay, can you see every strongly connected component is like a family? Can you notice? Every strongly connected component, every strongly connected component is like a family. Yes or no? Is like a family. Is like a family. Correct? It is like a family. Every strongly connected component is like a family. For example, let's assume this is a family A, B, C, D. Then they are strongly connected to each other. See, they are strongly connected to each other. Yes or no? They are strongly connected to each other and it is maximal. What is the definition of family? What is the definition of family? Family is also maximal if you notice. What is the definition of family? Can anyone tell me? What is the definition of family? Let's assume that this is mother, this is father, this is boy, this is girl. Can I say this is family? Mother, comma, girl. Can I say this is family? Can I say this is family? This is not family. Family is maximal. Okay, something like this. Yes or no? This is the analogy. See, this is not family, mother, comma, girl. Basically, family is a maximal. I can say this maximal. This is family. I can say family is maximal group of members who are strongly connected to each other. Okay, who are strongly connected to each other. Strongly connected to each other. Family is basically a maximal group of members. This would be maximal. A maximal group of members who are strongly connected to each other. Now, so this, if you notice, this strongly connected component is like a family. Okay, so for example, these are, now can you notice one more thing? Please notice one more thing. Let's assume this is the family. So this is your strongly connected component 1. This is strongly connected component 2. Is it possible? This is strongly connected component 2. This is strongly connected component 1. Like this is a family. This is maximal. This is a family. This is maximal. Is it possible that B, D are strongly connected? Is it possible? Is it possible that B, E are strongly connected? That they are strongly connected? Is it possible? Is it possible they are strongly connected? Is it possible? The answer is no. The answer is clearly no. Why? What is the reason? What is the reason? Because if they are strongly connected, then this whole thing will be a family. There will be, okay, then this will become a family. Yes or no? Very simple. See, if they are strongly connected, then automatically everything will be strongly connected because they are strongly connected. So everyone will become strongly connected. So you can notice that if they are strongly connected, then you will get then they will merge. The answer is no. Why? The answer is no. Why? What is the reason? Okay, because if they will basically merge, the idea is very simple. So the answer is no, because else they would merge. The answer is no. So answer is no. Else they would merge. Else they would merge and make single strongly connected component. Make single family or strongly connected component. So this is the idea. Now you can notice that every strongly connected component is like a family. So can I represent it by one family? Like, okay, what you do? This is like a family. So you represent this by one vertex. What you do? You shrink it. These 4 vertices, you shrink them and you, okay, represent them by one family F1. You represent them by S1 and you represent them by S2. You shrink them. Okay, these 4 vertices you shrink and okay, you make one vertex. Okay, like it's like you shrink them and you make one vertex with one family, and you shrink them and you make one family. So this is the idea. What to do in a directed graph? if we shrink, okay, if we shrink each strongly connected component down to one single node, okay, and then draw, how to draw an edge between two of them, edge between two family, edge between two strongly connected, if there is an edge between some node in first to some node in second, okay, then we call the new graph, that you will get, the new graph, we will call it associated directed acyclic graph. I will tell you why. I will tell you the reason why this is associated directed acyclic graph. Why this is acyclic, I will tell you the reason. But this new graph will be called associated DAG. This new graph, we will call it associated DAG. Let's understand this concept. Let's understand. So for this, find associated DAG. Let's find associated DAG. For this graph, find associated DAG. Let's find. So this is your graph G. In this graph G, let's find out associated DAG. So what I will do, see, very simple. What I will do, you can notice this is a family. This is a strongly connected component. There is a cycle. So this is a strongly connected component. What I can say this is a strongly connected component. So let's call it S1. This is also a strongly connected component. Let's call it S2. And this is also a strongly connected component. Let's call it S3. Then what is the associated DAG? It simply means that you make families, S1 family, S2 family, S3 family, S1 family, S2 family, S3 family. Now you can notice there is edge between from S1 to S2. Why? Because this person is friend of this person. Like I can say this person is related to this person. This edge is because of whom? Can anyone tell me? From S1 to S2 there is edge because of this. Because of this 2,4. Yes, very good, very good. Because there is 2 here, there is 2 here, there is 4 here. Because of these two, this is the edge. Because of these two, this is the edge. There is 2 here, there is 4 here. And you can notice there is edge from S2 to S3. There is edge from S2 to S3. And this edge is because of 6,7. Because of 6,7, this edge we have. Is this clear? So finally, I can say that this is the associated directed. Can you notice this is acyclic graph? Can you notice this is acyclic graph? Can you notice this is directed acyclic graph? Did you understand this? Did you understand this concept? If we shrink each family, each strongly connected component, we shrink down to be one vertex. Okay, we shrink it to one vertex. And when do we put edge? Edge we put if there is an edge from some vertex in the first to some vertex in the second. Then this new graph we will call it associated DAG because it is acyclic. This new graph will be acyclic. Let's see this question. Find associated DAG. Let's find out associated DAG. For this, don't worry, I will answer all your doubts, but find associated DAG. So what that will be? Find associated DAG. Very simple. This is one family. You can notice this is one family. So I can say this is a family S1. This is another strongly connected component. This is another strongly connected component. So what will be the associated directed? Okay, so that will be S1, S2, S3. You can notice there is edge from S1 to S2. There is edge from S2 to S3. Or you can understand like this. You can understand like this. See, you can understand like this. Make one vertex for 0, 1, 2. Make one vertex for 0, 1, 2. Make one vertex for 3. Make one vertex for 4. Now you can notice that there will be edge. There will be edge from here to here because of 0 to 3. Because of this. So because of 0, 3 there is edge. And from 3 to 4 there is edge. You can notice this is you can notice this is directed acyclic graph. If you notice, there is no cycle. This is directed acyclic graph. Let's see this question. In this question, what will be the associated DAG? What will be the associated DAG for this? That will be a single vertex. that will be a single vertex 0, 1, 2. A single vertex. You will get a single vertex. Basically, you will get a single vertex. I can say this will be your associated DAG. If you call it S1, then this will be your answer. Okay, this will be the answer. So this concept is clear. Next, what about this? Find the associated DAG. Associated DAG. What that will be? Find the associated DAG. So again, you can notice that this is your strongly connected component S1. This is a strongly connected component S2. This is a strongly connected component S3. This is a strongly connected component S4. So what is associated DAG? That will be like this. A, B, C, D. There will be F. There will be G. There will be H. There is H from this to F. There is H from F to G. There is H from F to H. Also, there is H from G to H. Okay. So can you notice this is also directed acyclic graph? If you notice, this is also directed acyclic graph. Is this clear to everyone? This is the associated DAG. Next, what about this? What is the associated DAG for this? What is the associated DAG for this? This itself. Okay, associated DAG, same. G itself. I can say G itself. G itself is the associated DAG because this is already DAG. If you notice, this is already a directed acyclic graph. So actually, these are the, if you notice, these are the strongly connected component S1, S2, S3, S4. So these are the strongly connected component. You will get the same. This G itself you will get. What about this? This is your graph G. Find the associated DAG. Find associated DAG. What that will be? First, you find the strongly connected component. This is a strongly connected component S1. There is a cycle here. So this is a strongly connected component S2. This is a strongly connected component S3. This is a strongly connected component S4. This is a strongly connected component S5. S5. This is S6. This is S7. So total you have 7 vertices. Yes or no? Total you have 7 vertices. So in this total you will get 7 vertices you will get. Total you will get total 7 vertices you will get. So the answer that you will get will be like this. See, associated DAG. The answer you will get will be like this. S1 from S2 to S2 there is S1 to S2 there is age. There is age. From S4 to S5 there is age. From S6 to S7 there is age. And from S7 to S5 there is age. And there is S3. This will be the answer. Yes or no? Can you notice this is also DAG? Can you notice this is also directed acyclic graph? This is also DAG. Clear? Is this clear to everyone? Anyone has any doubt in this? Let me know. So this is the final point. If you shrink, you will get a, remember, you will definitely get a DAG. Remember, you will definitely get a DAG. Why? What is the reason? This is my question. Why we get DAG? Why we get directed acyclic graph? When we shrink, basically, okay, why we get directed acyclic graph in the previous problem? In the previous problems, why we get directed acyclic graph? The concept is very simple. See, if you don't get directed acyclic graph, first of all, you notice every vertex is what? First, you tell me every vertex is what? Every vertex is what? A strongly connected component. Every vertex is a strongly connected component. This you already know. And a strongly connected component is maximal already. And this is maximal already. This is already maximal. You cannot make it bigger. You cannot make it bigger. Now, if you don't get, if you get cycle, by chance, if you get cycle, by chance, if you get cycle, then what is the problem? Like if you get this type of cycle, let's assume this type of cycle you get. If you get this cycle, then what is the problem? Then you can merge into one. If you get this cycle, then what is the problem? The problem is that now you can, you not, okay, if you get this cycle, what it means? It means these were not maximal. It means if you get cycle, then it means these were not maximal. These were not maximal. There is a contradiction. These were not maximal. So contradiction. So you will definitely get a directed acyclic graph. Okay, if you get a cycle, it simply means that these were not maximal. These were not maximal. These could have been merged. Could have been merged in original G. These could have been merged in original G. I can say these were not maximal in original G. So there is a contradiction. Okay, please tell me, is this concept clear? So remember, this is a very simple idea. If you shrink each strongly connected component, if you shrink each strongly connected component down to one vertex, and you put an edge from some node to first of, okay, then some node, then this resulting graph will be a directed acyclic graph. And the reason is very simple. What is the reason? The reason is very simple, that if you have a cycle of strongly connected components, then you would have merged them all to single. Okay, so finally, this is the line. This is the statement. I can say every directed graph is DAG of its strongly connected component. This is the statement. This is the theorem. Every directed graph is directed acyclic graph of its strongly connected component. Did you understand this? Every directed graph is a DAG of strongly connected components. I hope this concept is clear. Very simple concept. Like, what is the associated DAG now for this graph? What is the associated DAG? What that will be? Let's find out the strongly connected component of A. Always do like this. If you don't want to make a mistake, always do like this. Let's find out what is the strongly connected component of A. You can notice A will be there, B will be there or not. From A to B we have, from B to A also we have. So B also will be there. So B also will be there, C also will be there. So okay, B also will be there, C also will be there. B also will be there, C also will be there. Now think about it. Think about it. D will be there or not? Think about it. D will be there or not? There is no path from D to A. Check it. There is no path from D to A. So D will not be there. F will be there or not? F will be there or not? There is path from F to A. There is path from A to F. There is path from F to A. There is path from A to F. So F will be there. Okay, tell me, H will be there or not? H will be there or not? No, because there is no path from A to H. There is no path. So this is the idea. Okay, always do like this. Always do like this. So I can say that this will be your strongly connected component S4, and this will be your strongly connected component S5. So number of strongly connected component, that will be 5. So in the associated DAG, you will have 5 vertices: S1, S2, S4, S5, S3. So you can notice from S2 to S4, okay, and from S1 to S4, and you can notice that from S4 to S5, from S4 to S5, and from S4 to S3, S5 to S3. So this will be your graph, correct? Yes or no? Okay, let's see this question. This is a university exam question. So find associated DAG. Do systematic. Let's find out the strongly connected components of A. So A will be there. What else? You can notice this cycle. You can notice this cycle. So A will be there, B will be there, E will be there. Can I add C? Okay, can I add C? See, from A to C you have, but from C to A, can you go from C to A? Can you go from C to A? No, you cannot go. You cannot go from C to A. You cannot go. What about D? Can you go from D to A? Can you go from D to A? No, you cannot go. Okay, so you cannot go. So I think only this will be there. Okay, so A, B, E. This will be your graph. So this will be strongly connected component 1. Next, what is the strongly connected component of D? What is the strongly connected component of D? D will be there. You can notice this cycle. Notice this cycle. Notice this cycle. So DGH, DGH. Can I put I? Tell me, can I put I? There is path from D to I. There is path from I to D. So yes, I can put I. Okay. And you can notice that. You can notice this also you can put. Because of H, you can put HFI. You can put F also. So you can put F also. Okay. So finally, this graph you got. Nothing else you can put. Nothing else. This is your strongly connected component 2, and this is strongly connected component 3. This is the strongly connected component 3. You can just check it. Okay. So finally, this C, it will only have C. No other vertex can basically no other vertex is strongly connected to C. So finally, your number of, I can say number of strongly connected component is 3, and the graph you will get will be like this: S1, S2, S3. The graph you will get like this. From S1 to S3 there is age. From S1 to S3, from S1 to S2 also there is age. Next, from S3 to S2 there is also age. Nothing else. Okay, nothing else. Remember, in the exam they will give you this. They will not give you this. Actually, what they will give you, they will give you this. In the exam, they will give you, they will write the vertices. S1 means ABE. S1 means ABE. And you can notice S2. S2 means DG, this DGHIF. And S3 means C. So in the exam, they will give you like this. This is the DAG. You can check, this is the directed acyclic graph. Okay, so that's it. Tell me the answer for this. Quickly tell me how many strongly connected components you have in this graph. So you can notice this will be one strongly connected component. This is one strongly connected component. You can check. You can check. This is one strongly connected component, S1. What next? What is the next? So you can notice that this is another strongly connected component S2, and this is another strongly connected component S3. This will be S3. So total 3 components you will have. Okay, number of strongly connected component, that will be 3. Yeah, it is already marked. Okay, so let me remove. Okay, actually an associated DAG, what that will be? Associated directed acyclic graph, what that will be? That will be like this. That will be like this: 0, 1, 2, 3, 5, 4, 6, 7. 4, 6, 7. So finally, what you will have? From 4, 6, 7 to this, you will have. From 5 to this also you will have. From 5 to this also you will have. And from 5 to this also you will have. Okay. This is your DAG. You can check. This will be your DAG. Okay. So the answer will be 3. What is the answer for this? Number of connected components. How many connected components in this graph? The answer is only 1. This is undirected graph. Remember, this is undirected graph. This is your undirected graph. So because this is undirected graph, so this is your one component. Only one component you have. What is the answer for this? Again, this is undirected graph. Okay, this is undirected graph. Because this is undirected graph, how many components you have? Total 2 components you have. Okay, here you will have 2, basically A, B, C, D, E, F. So there are 2 components. A, B, C, this is one component, and D, E, F, this is another component. So this component, total 2 components you have. This question you can take as homework. Okay, so for this question you have to find number of strongly connected components and also associated DAG. Okay, so you can take this as a homework because many questions we have done. Yes or no? This is another homework. Already many questions we have done.